All right, thank you so much for joining us today. So in this video, we are going to talk about non-homogeneous second order differential equation. So in the last 4 videos, we spent time talking about homogeneous second order differential equation. And that one is a very key to help us to learn non-homogeneous second order differential equation, because we saw that the homogeneous differential equation is when we let ay prime prime plus by prime plus cy is equal to 0. So always we are going to use this. Always we are going to solve for the homogeneous aspect before we can think of adding the non-homogeneous aspect to it. So basically that is what we are going to do, right? So with this one, we are saying that the differential equation is equal to a function g of x, right? And that if that's the case, then what are we going to get? So if that's the case, and then it means that here we are going to have two solutions. We are going to have something called complementary solution, and we are going to have something called particular solution. And when we add these two solutions together, we are going to call it a general solution. So that is what we are going to do. So we are going to start the idea that when I solve the homogeneous aspect, when I let ay prime prime plus by prime plus cy is equal to 0 and solve it as we saw from the last 4 videos, we are not going to call it a general solution because of this. So when I solve it and I get my root, let me say m1, m2, and I want to write the general solution. So let me assume that my general solution from the previous video was c1 y1 plus c2 y2. Now, this is not a general solution because the function is not equal to 0, it's equal to g of x. So we are going to call this a complementary solution. So I put some yc here telling me that this is a complementary solution. Now, when we are done, we need to use this here to find another solution, which we are going to call it a particular solution. Now we will go through the process of learning how to find a particular solution. So we always find this using the homogeneous aspect of the equation. Now what should we learn? Now note that anytime you see yc, we are talking about the complementary solution, and this complementary solution is coming from the homogeneous solution. So y prime prime, y prime plus cy is equal to 0. So always we get the complementary solution from the homogeneous aspect. Now with the particular solution, I'll go through the next slide how we can get the particular solution. Now after I've gotten the complementary solution and particular solution, when I add these two together, then I'm going to have the general solution. So this is what we are going to add up. So you see that very good with this one. All we just need to add up to this is now we need to look at how we can find our particular solution from this case. Now let's go through the process of finding or solving non-homogeneous second order differential equation. Now the method that we are going to talk about in this video, we are going to talk about two methods. We have a lot, but we are going to just look at two of them. And the first one that we are going to look at is the method of undetermined coefficients. It's very simple, and I'm going to show you how you are going to go through this process. So the method of undetermined coefficient is after we have gotten the complementary solution, then the method of undetermined coefficient will help us to find for the particular solution. Now, we are going to look at how to find a particular solution, but this is how we can use the method of undetermined coefficient. So after I have assumed my particular solution, then what I need to do is I need to differentiate my particular solution, that's y of p. So you see that the differential equation is in terms of y prime prime, y prime, and y. So if I assume that this is my y, then I will need yp prime and yp prime prime. Then I just go and do substitution from this one, like what we were doing in the previous videos. after we have assumed that y is equal to e to the power mx, we need to find y prime and y prime prime and just do substitution. So basically that's what we are going to do. So after I'm done differentiating, I'll plug yp prime yp prime prime into the original equation. The original equation that we are talking about is this. Good. And we go through the process. Then we match the terms and then we solve for the algebraic equation for the undetermined coefficient. Now let's talk about how to find the particular solution, the guesses, right? We need to guess the particular solution. So this, I'm going to help you to, whenever you see the non-homogeneous differential equation, after you found your complementary solution, how you can guess your particular solution so that you can take it from there. So first, we are assuming that if the non-homogeneous equation is this, it's in terms of exponential function and the coefficient here is constant, then this is what we can do. So here we can see that the gen of x is equal to what is here. Then the first thing that we need to do is we need to suppose that this is equal to 0, what we learned. And then what we are going to do is we are going to assume that m1 and m2 are the characteristics root. Then if that's the case, and this is the exponential function, then the first thing that we can assume is, now we are going to assume that this alpha here, which is the coefficient of x here, right? Whenever this coefficient of alpha here is not the same as m1, it's not the same as m2, then we are going to consider a trial solution. Which trial solution are we going to consider? We are going to consider a trial solution, which we are going to call it yp, which is equal to a e to the power alpha x. So this is a trial solution that we are going to consider when alpha is not the same as any of the roots. So you see the idea of homogeneous second order differential equation playing a role here. So here we need to be able to go through finding our m1 and m2. Then we compare the coefficient of x here, which is alpha, to the roots and see. So if they are not the same, then this will be our guess for the general solution. Now, let's assume that one of the alpha is the same as m1 and the other one is not the same as alpha. Then what will be the guess solution? The guess solution is very simple. Our yp should be the same as a, but here we are going to multiply it by x because one of them is the same as this. And you understand when we are taking example, this is going to give us this. So since one of them is the same as m1, we multiply by x. So this will be the guess solution when one of the roots is the same as the coefficient of the alpha x here. Now guess what? What if alpha is the same as all the roots? Alpha is the same as m1 and m2. It means that m1 and m2 are the same. Because if alpha is the same as m1 and m2, it means that they are the same. Then it means that we are going to guess a particular solution of the form ax squared. So this one is not difficult to know them. Whenever none of them is the same as the root, you just have a constant times this, a constant times this. And then whenever one of them is the same as that, you have x, a constant, and then the function. And when they are all the same, we have something like this here. So basically that is how to go through when the function is exponential function. I mean, the non-homogeneous aspect gen of x is an exponential function. Let's take another case. Now let's assume that the non-homogeneous aspect is not exponential, but it's a polynomial function. Then what are some of the things too that we are going to consider, right? So anytime it's a polynomial function, we consider the idea that m is equal to 0, right? M is equal to 0. That's what we are going to consider. But here we are assuming that m is not 0. So m here is like the degree, right? So now what we are going to do here is, now we know that this is a polynomial function, and we are assuming that the non-homogeneous aspect, what is the gen of x, is the same as a polynomial function, right? Then we go through the same process again. We assume that the homogeneous aspect is going to give us m1 and m2. Then the first thing that we want to do is we consider when m is 0. You understand it better when we are solving the example. So when m is equal to 0, then we are assuming that, okay, let's assume that m1 and m2 are not the same as m, meaning that m1 is not 0, m2 is not 0, and m1 and m2 are also not the same. If that's the case, then we are going to consider a trial solution. This is how we are going to consider the trial solution. So yp will be equal to a naught plus a1 x1 x to the power 1 plus a2 x squared up to an xn. So it depends. For us to consider this trial solution here, it depends on the degree of the polynomial function here. So if the degree of the polynomial function is to the power 2, then we will move up to the second order. If the degree of the polynomial here is just 1, then we are going to have a linear function. So we are going to take example and you understand it better. So anytime m is equal to 0, I said always we are going to assume that m is 0. So whenever it's not the same as any of the roots, this is how we are going to write our particular solution, or we are going to guess our particular solution. Now let's assume that one of the roots is equal to 0 and is equal to m, and one of the roots is not 0, which is not equal to m. Then what will be the particular solution? We are going to guess this to be, we are going to multiply this one by x. So anytime one of them is equal to one of the roots, we multiply it by x. So this one is going to be a naught plus a1x plus a2x squared up to an xn. And as I said, this would depend on the degree of the polynomial function of the non-homogeneous aspect. So this is what we are going to get for considering when one of the roots is the same as m. And then guess what will happen when m1 is the same as m2 and it's equal to m? I mean, all of them are 0. Then basically we are going to have yp to be equal to x squared a naught plus a1x plus a2 x squared up to an xn. So they are very simple to keep. So now we've learned exponential function, we've learned a polynomial function, how to go about them. So you should be knowing how to, guess the trial solutions, right? I'll show you more tricks when we start solving examples. Now let's look at another one. Now let's look at combining exponential function and polynomial function, right? So exponential function and polynomial function. Now when we started with the exponential function, I said this is a constant. So this one cannot be x. Anytime you have x e to the power alpha x, this is a combination of a polynomial function and exponential function. So this one should be always a constant, like 2e to the power alpha x. Good. So now we want to combine exponential function and a polynomial function. Then what will be the trial solution? What will be the particular solution, right? So let's look at the trial solution. So the same thing that we are going to go through, we solve the homogeneous aspect. We compare m1 and m2 to the alpha. So anytime you have exponential function, we compare the m1 and m2 to the coefficient of x here. So let's start by assuming that they are not the same. Alpha is not the same as m1, it's not the same as m2, and m1 also not the same as m1 and m2. Then what will be the trial solution? So the trial solution here is going to be yp is going to be e to the power alpha x, then a polynomial function. So we saw that, good. So we saw that when it is when it was only exponential function, we have this and less a constant. So the constant is just here. So when I assume that this is a constant and this one is going, you see that we go back to the original function when it is only exponential. But anytime we have a polynomial function, then we are going to multiply this one by this. And this would depend on the order of, or let me say the degree of the polynomial function here. So the same idea there. Now let's assume that one of the roots is the same as m. Then guess what will happen? Then our yp, that is our trial solution, is going to be x. So I'm just going to multiply x by this. That's all. So x e to the power alpha x a naught plus a1 x plus a2 x squared plus up to an xn. That's what I'm going to get. And guess what? What if all of them are the same? Alpha is the same as m1, is the same as m2. Then I just multiply this one by x. So that's basically what we are doing here. So I'm going to have yp is equal to x squared this a naught plus this x up to an xn. So this will be the trial solutions. And as I said, we will solve more when we are dealing with the examples. Now let's look at another aspect. Let's look at when we have exponential function and trig function. So trig function, we are looking at the sine and then the cos, right? So we are looking at the idea that the non-homogeneous aspect is in terms of a trig function, right? And somebody will ask, let's assume that gen of x is equal to cos s, but we are saying that it should be in terms of this exponential function and this. So here, anytime we see something like gen of s is equal to cos s, then here is the same as e to the power 0 cos x. So this one goes together. So you see that I didn't talk about whenever it is in terms of only trig function, because if it is only in terms of trig function, then the exponential function is e to the power 0 and tells you that alpha is 0 straight from there. And when I'm taking an example, I will show you how to do that. So if the non-homogeneous aspect is a trig function and exponential function, it's either this or this, then this is the trial solution that we need to assume. So we assume that m is the characteristic root, and we know that here m is going to be something like this. Let me say u plus or minus I v, right? Because it's a complex. So anytime we have something like this, then we need to think about complex, right? So then what will be the trial solution for this one too? So you can see that here what we just need to do is, here too we need to compare m to this, right? Because when we solve this, we are going to have a complex numbers like this, and then we can also write what is here in terms of complex. So the alpha plus or minus I beta is coming from the equation that they are going to give it to you. For example, this here means that alpha is 0 and beta is equal to 1. So compare this one to this. So as I said, you can write it in this form. So you see that alpha here is 0 and then beta here is 1. So this one helps you to write this. And then the m here is when you solve the homogeneous aspect and you are getting it in this form. So here we are assuming that this is not the same as this. I mean, alpha is not the same as beta, mu, and then beta is not the same as v here. So basically that's what we are doing. And it can be that alpha is also the same as this. But as soon as beta is not the same as this, they are not the same. So for example, if I have 2 plus or minus I, and I have 2 plus or minus 2i, these are not the same. So that is when we can consider the trial solution for this. So anytime they are not the same, then this is the trial solution. Yp will be equal to a alpha s cos beta x plus b e to the power alpha x sine beta x. Now who can tell me this? Now you see that this one, if I factor e to the power alpha x out, it will be left with a cos of beta x plus b sine of beta x. And you will see that this particular trial solution here was the trial solution that, or let me say yes, the trial solution that we were talking about when we were dealing with complex, right? So when you consider the homogeneous aspect and you find the, let me say, the root, the characteristics root, this is the homogeneous, or this is the general solution that we write. And that is what is basically the same as the particular solution here. When this and this are not the same. When they are not the same. Then we are going to assume when they are the same, right? Alpha is the same as u and beta is the same as vin. Now what we just need to do is just multiply x by this and then you are done. So I'm just going to have my trial solution to be x times a alpha s cos beta x plus b e to the power alpha s sine beta x. This will be the trial solution. So as I said, it's kind of complicated, but as soon as we take examples, you will see that it's very, very simple. And sometimes you don't need to even record this. All you need to know is know how to write, let me say, the trial solution, and remember the first one. Don't remember this one too. Just record the first one here. This one to just record the first one here. The second one is just multiplying this one by x. And then if you want to go further, multiply by x squared. The same thing applies to this. Just remember this. The rest is just multiplying by x and x squared as it goes. And the same thing to the exponential function too. Remember this. The next is to multiply by x and x squared as we are moving on. So yes, this one will help us to solve all the guesses. We can guess it. So all the particular solution that we've done here, all the guess that we are making here, this guess that we are making here, we are going to use the idea of method of undetermined coefficient to solve. So all the guess that you are going to do, anytime you guess a particular solution, we use method of undetermined coefficient to solve it. Now let's look at the second method. Now, anytime we are looking at this second method here, we are not going to do this guess that we are doing here. We are not going to use case 1, case 2, case 3, and case 4. We are not going to use them. Method of variation of parameters has its own way of guessing the particular solution. So basically, that's what we are going to look at. So the method for undetermined coefficient is the one that we went through. So when you are taking example, I'll show you. Good. So now the same thing with method of variation of parameters. We solve the complementary solution by solving the homogeneous aspect. And when we get the complementary solution, now this is what we are going to do with method of variation of parameters. We are going to assume that y1 and y2 are linearly independent. It means that it has a determinant which is not equal to 0. I mean, when you pick the Wronskian, it's not equal to 0. You understand them, the terms that I'm talking about. So this is independent. If that is so, then we can use the method of variation of parameters. What are we going to do? We are going to assume that this constant here, C1 and C2 here, are in terms of x. So that's how we are going to rewrite it again. So now we are going to assume a particular solution which takes the form. So you can see that this now moving from yc to yp. The only difference here is we have y1 here, y1 here, y2 here, y2 here. But the only difference here is c1, u1, c2, u2. And the only difference here is this is constant and this is a function in terms of what? X. Good. So that is basically what we are doing here. So now as soon as we get this, this is what we are going to look for. We are going to look for u1 and u2. Then we add it to the complementary solution to get the what? The general solution. So after adding this to this, then we get the general solution. Let me guide you through some of the things that you need to get from here. So anytime I need to look for u1, so when I set this, right? when I finish finding my complementary solution and I set it in this form, that's what I'm going to do. U1 is equal to minus. So I just did the proof and then I had the formula. So I just want to give you the formula, then you'll be using it. So U1 is equal to y2 of x, then gen of x divided by the Wronskian of w. I'll show you the Wronskian very soon. Then u2 of x is equal to integration y1 of x gen of x divided by the Wronskian of this, the x. Now what is y2? Y2 will be always in here in the complementary solution when you are done using the homogeneous second order. And then y1 is also always here when you are done finding your solution for the complementary aspect. Then what is gen of x? Gen of x is always given here. This is the gen of x, the non-homogeneous aspect. That's what we call it, the gen of x. Then the only thing which is left is the Wronskian, that is w of x. Now w of x, we are calling it the Wronskian, right? And this is basically the same as, now the Wronskian is finding the determinant of your solution. So y1, y2, right? So the solution that you had here, y1 and y2. So since we are building a 2 by 2 determinant because the solution is 2, then y1 here, y2 here. The one that are going to be here is just taking the derivative of this and taking the derivative of this, putting them here. So this is going to give us y1 prime and y2 prime. So this is the Wronskian, right? We will solve an example and we'll see how you can go through them. So please master or write down this formula somewhere, and then remember this form 2, and then remember the Wronskian. So this is the end of the video. Yes, this is the end of the video. So this video was basically teaching you everything that we are going to do in the next video. So in the next video, we are going to take example, and this is how I did it. I'm going to start with case 1, right? I'm going to start with case 1. So we practice a function which is an exponential function. I mean, the non-homogeneous aspect is equal to an exponential function. And remember, whenever we are using case 1, case 2, and case 3, and case 4, we are going to use the first method of undetermined coefficient. So we are going to also learn it from there. So that is basically what we are going to do. When we are done going through all the cases, then we are going to take example on method of variation of parameters. Then we will be done with non-homogeneous second order differential equation. So see you in the next video.